Hello everyone, welcome to the recap show for our second ever Visibility Jam. So glad that you are all able to join us today. I've been really looking forward to this jam and this recap show for a while now. As I mentioned, this was our second ever Visibility Jam. And you might wonder, if you haven't been around the community, what does visibility mean? Well, the idea of the Visibility Jam is to take something in your computer, something that is like some technical information, some metrics that aren't usually visible, or details about some algorithm, or, whatever it happens to be that is there, but that hasn't really been made visible to you yet. It's a really interesting topic for this community because the handmade community is about deeper understanding of systems, learning how systems really work, gaining that rich understanding, and using that to build better software. And so the first step in that process is to actually somehow get at the information and understand it so that you can build better high-level software with it. Now, we had 16 wonderful submissions to this jam this year. You can see all of them on the jam page, and if you do !jam in the chat, you will get the link that Asaf also just posted in the chat. Thank you, Asaf. We are going to interview 6 of these project creators today on this show, and I'm really excited to get their thoughts on, what inspired these projects, where they're going to take it from here. It's going to be a really great time. And so, really, without any further ado, we're going to jump over to our first interview. So, the first guest that we're going to have on is BYP, or Billy Pan. And those who have been around the community for a while will know exactly who Billy is. He, the first really major thing that I remember him doing, like publicly, he demoed a project called SDF Atlas at Handmade Seattle in 2022. For last year's Visibility Jam, he created a project called Ready, REDE, which is like an IDE for regular expressions. And this is a perfect example of that visibility topic. It shows both the structure of an NFA that matches a regular expression, or that actually executes a regular expression, and shows you the execution state of it as you match it against a string. It's such a cool project, and it actually really kind of blew up on Twitter when he posted it. But I am pleased to say that Billy is back this year with another project about algorithm visualization. So, there we go. I found my OBS scene. Welcome to the show, Billy, and welcome back to the Visibility Jam. Thank you for submitting your project.
Yeah, sure.
So, you did for this jam like I said, another project about algorithm visualization. So this time, though, it's about detecting cycles. And let me switch over to the scene that has the actual screen share here. So this is your project Loop-de-Loop. And can you just give us a brief demo and sort of tell us what it's about?
Yeah, sure. So you have this sort of list here, and then I've made a cycle for it. And so you can control how long that start of the list is and how large that cycle ends up being. And then the question kind of becomes, if you're only allowed to traverse the list, right? This is sort of a human perspective of the list. If you're only allowed to traverse it, node by node, how do you find where that cycle is? And so the sort of standard way is to literally just store every single node that you've ever seen. And if you've ever seen a node twice, that's where the cycle is. And that just means you have to store every single node in the list again, which for some cases is intractable. So there are other algorithms that you can do. So one thing is you can just say, every time you're about to visit a node, traverse the list up to where you were and see if you're going to visit something. And that just means you have to do it in n squared. And so then the question is, can you do it without that storage requirement, but also better than n squared? And so those are like sort of pointer cycle detection algorithms, which I wanted to visualize here. And so the first method is what's called tortoise and the hare, where we're going to have these 2 nodes here. And the purple node is going to move at 1 step per iteration. And then this pink node is going to move at 2 steps per iteration. So the purple one being the tortoise, the pink one being the hare. And then if we just let them play out, right, you're going to have them sort of run in this circle and collide. And then from there, using a bit of algorithm information, we can find out, how to compute those between there. And so that's what's called Floyd's algorithm. It's showing at the bottom and how many steps. And then the other one was going to be Brent's algorithm. And so that one is slightly different, where instead of moving at different speeds, we're going to just keep trying new start positions every power of 2. And then we're going to try those. And then once we find the collision, the only way we get a collision is if it starts inside the loop. And so then we can just count how many times it takes, and we get the length of the loop, and then a similar sort of way that we can extract the start using that information. And so you can try different loop lengths, and you can sort of control, I sort of have it highlighted here, sort of these key points in the algorithm. So here are like the different powers of 2 that it tries. And then once it actually finds it, it shows you that part, and then it computes that last part there. Is the basic overview.
That is wild. So, I mean, a couple questions. So, to back up a little bit, I think I had heard of the tortoise and hare thing before, sort of, I think, as a like interview trivia sort of thing. But what I didn't realize was that you could use that information to actually detect the length of the cycle. Could you go back and dig into that a little more? Because you have this interesting view of sort of the spokes, and it's like the algorithm keeps running after the cycle is found. But how exactly does that work? Naively, I'd think you're just going in circles at that point, and you don't really know where anything started.
Yeah. So the simple way that I had sort of initially showed was once you have this intersection point, and I'll make it a little bit easier to see. So once you have that intersection point, here, you could just say, all right, hold one node in place and then just go do another lap, right? And that, if you count how many times it takes, that tells you the length of the loop at that point. And then that would be fine if you only wanted the length. But if you also wanted the start position, you can basically dissect it. I'll switch over to this one because this one's actually easier to explain. So once you have the length of the loop, if you want to get back the start information, there's sort of two things you can say, right? We want to be able to traverse the start, and we want to get to this sort of starting node here. And so there's two ways that we can sort of get there. We can either go exactly what I call S steps in this variable, or you can go S plus L steps. Those will both get you to that exact node in the loop. And so one thing you can observe is we don't actually know what S is at this point, but we do know what L is. And so we could say the equivalent of going S plus L is actually to go L plus S. That, if you're only counting the amount of steps, those are exactly the same amount. So if you go L first, then you can sort of count S afterwards. So that's what this part shows here, where you go L steps. So you can kind of see that this purple node is going to go exactly one loop, and then that is exactly L steps, and that's where we have that.
And the L steps are done. So you go another loop starting from wherever you detect the cycle, and then
we go. We're going to reset here and then go L steps. Yeah, we start at the beginning.
Oh, I see. Okay.
Yes, because you're going to go if you wanted to get to this node here, if you go S steps first, you'd get there. Or if you go S steps plus L steps, that would do another wrap. I'm only visualizing this to sort of show that it is exactly L steps. I didn't have another great way of visualizing that.
Sure.
But then once you're there, if you reset the pink node and the purple node, then they're both S steps away from this node. And so you just need to count until they collide at that exact part there.
Neat.
And that's how you count it from there. So that is if you sort of do the math and you count, right? This part here is going to take L steps, and this part here is going to take 2 times S steps, because we're doing S steps on the purple node and S steps on the pink node, so it's twice that. The thing about Floyd's algorithm is, and the reason that I was showing it here, Floyd's algorithm for doing this is slightly different. Once we get this intersection node, I just immediately count S steps. And that just comes from the way that you have to do the counting initially, which is that at the very first part, right, if we look and we say, all right, take S steps, right? At this point, the pink node is S steps ahead of the purple node. It has to be. It'll be S modulo the size of the loop. So if the loop is smaller, you have to do so many reps, but it'll be fine.
Because it's moving at twice the rate of the,
Yes.
Okay.
And so the next thing is to observe that the distance between them is actually the amount of steps it'll take for them to collide, or the amount of iterations it'll take to collide. And that's because the pink one moves at twice the speed as the purple one, which means every step you actually make one step of progress. The distance between them decreases by exactly one, right? Because they're the difference in their rate, right? If one of them's moving at 2x, one of them's moving at 1x, each one gets 1x difference. So that is the amount of steps it takes. And so that's when they collide. And so then that tells you that it's actually flipped, right? So here, the difference is s steps ahead, or s modulo L, and this is just the composite of that. And so then when they do collide, here, now we're actually the composite ahead, which means that whatever we're left with is s, right? S modulo L. And so if we do that same thing where we reset them both and then track them, we get s immediately. So it's like a very small. It just changes one constant factor of one of the things, but it does decrease the total number of steps.
Yeah.
It's a little hard to visualize that aspect of it, but it is. I have a diagram on the project page, so if people want to look at that, that'd be the place to go.
I have to ask, what prompted this? Was this just an algorithm you thought would be cool to visualize, or were you actually working on a project that required you to do cycle detection of some kind?
Honestly, I was just going over, like, just reviewing data structures and algorithms, sort of like from the very beginning. So you start with arrays and you go to linked lists. And the number one way that a linked list goes wrong is it has a cycle. And then the thing is, though, if you're starting from the beginning, you've only got arrays and linked lists. So you could just like keep appending to the array, or you could try to do something like the clever version is like a hash map, but you're not there yet. You don't have if you're starting way from the beginning, you don't have a hash map yet. And so if you want to do it without a hash map, it'd be something like this. And then sort of another thing was like being vaguely aware is that there's a Fabian Giesen blog post. It's just like 2 paragraphs, and it's called like cycle detections are handy to know. And he basically says like, yeah, everyone should know, these 2 algorithms. There's a Wikipedia page, it goes over it, and just go for it, for your own benefit. It's like, okay, I mean, well, I don't know them, and he says I should know them, and I trust Fabian Giesen on a lot of things, so might as well. And so the jam came around, and I already had this rendering, sort of project template from last year's jam project. So I was like, well, surely this will be easy enough to do in a weekend, and here we are.
Nice. Well, so, I mean, at this point, you seem to have a knack for visualizing algorithms. So are there other like data structures and algorithms kinds of things that you're thinking of exploring in the future?
Another interesting one is probably B trees, just because there's kind of like, so one thing is like in Handmade, there's kind of this idea of like, what data structure should you use? And it's like you have arena allocators with linked lists and linked lists with free lists, and then you have hash tables that are either open address and locally proven. There's sort of like this idea of like arrays are fast, but you can actually use linked lists if you know how you're allocating stuff. And it's like this idea of like memory granularity or cache line granularity.
Right.
And then there's also like this kind of a meme of like ECS and data oriented design and all that stuff. And then the question is just like if you look at ECS and you think of it in terms of just like database systems, right? You're querying a large swath of data in some sort of chunk cache line granular way, right? The sort of classic data structure for doing that is like a B+ tree. And then there's a question of like, well, how do those actually work? How do they balance? One thing that they're doing is they're trying to like pack as much into a single node. That way, when you get a node, you can you have it all in that single cache line or a single page. And then how do they grow? How do you get algorithmic constraints from there? And so that's actually one where I think it's pretty interesting. Oh, also there's this idea of like B tree insertion, lookup versus deletion. So you can actually give the entire structure of a B tree with all the invariants from only insert and lookup, right? That tells you everything you need to know. And then from there you can do like range query iteration. But then there's B tree deletion. How do you preserve balance invariance on B tree deletion, which CLR, the sort of classic algorithm book, does not cover. It just leaves it as an exercise to the reader.
Okay.
And it's quite tricky, right? If you delete nodes and you have to maintain invariance, feasibly, you'll have to delete all the way up to the tree, and it gets tricky from there. And so there are some other ways that you can do it, like lazy or relaxed deletions as well. Like there's a whole swath of things that are like super interesting about B trees that like, most people, oh, I use SQLite. Why do I need to, SQLite has its B tree. I'm sure it's fine.
Right.
we do that. And then I'll just stick with my arrays, my linked lists, and my hash maps. And surely we'll be fine. It's like, well, there are actually really interesting stuff here that like, it just kind of gets swept under the rug. And I think that'd be fun, but that's a lot more, it's a lot more of a problem to show those invariants visualized than just like simple cycle detection. But
Sure.
that's something I find super interesting.
Yeah. No, that would be really, really interesting. I mean, I hope that you find the time someday to do that. I think it'd be really cool. So I think that's all the time we have. We got to get to some of the other project authors. But thank you so much again for submitting this super cool project, and thanks for coming on the show.
Yeah, sure thing.
So the next guests that we have here, it's actually not just one project author, but two. So there was a bit of a running theme during this year's Visibility Jam of memory visualization, just sort of generally. My own jam project was one where I was trying to visualize some low-level memory info. Martin Fiel, the author of the Orca project, was working on like a WebAssembly disassembler and sort of annotated hex viewer. And then there were these two other projects, one by Khrob, one by Leddoo, and both of these were also digging into sort of memory structures in an interesting, different way. So we're actually going to have them both on at once here. We're going to have a little impromptu panel about memory visualization and their own individual projects in that vein. So welcome to the show, Khrob and Leddoo.
Hello. Thanks for having us.
So let's have each of you demo your projects briefly one at a time here. So Khrob, this is your project structure. And if you could just give us a brief explanation of that and show it off, that'd be great.
So, yeah, I didn't have a whole lot of time, but I knew the jam was coming up, and I wanted to have, I don't know, like I'm old enough to remember 8-bit machines. My first machine was a Z80, and you had a very limited amount of memory to look at, and you could basically lay it out on one block and go, okay, this is the video memory, this is the operating system's memory, this is how many bytes you've got to work with. And I've been seeing my nephews learning to program at school, and they're using Scratch and they're using Logo and really basic things. But something I feel Handmade has really brought home for me over the years is that computing is about how you change what's in one part of memory into another part of memory, and being able to visualize that. And it just so happened that in the week leading up to the jam, an old, well, not that old, but an Andrew Kelly session from Handmade Seattle came up that was talking about how he was rearranging his structures for better cache coherency and that sort of thing. And I thought, yes, that would be a really useful thing to be able to just go look at. I've got a struct here, and I'll write a struct. Could be could be for anything, but you throw stuff in, and you don't really think too much about it. But then when you understand what's going on under the hood, you need to know that if it is a short, that's going to be 2-byte aligned. If it's a 4-byte aligned float, then it's not going to just take the next thing. But it's all well and good to know that, but to be able to actually look around and see that, if I have these things in this order, I'm wasting in the order of 12 bytes here. So yeah, I made something that would parse a very, very simple struct. Like, you can't throw any old C at this. You can't put, it's a jam. But I wanted to be able to go, what happens if I move that around? Okay, if I put that there, that's fine, but I'm still at 32 bytes. But if I move this up here, suddenly I'm down to 24. And we can, and just being able to have that visceral feedback of what just knowing that order matters, and if you throw that there, okay, that's all right. But and so this is as far as I got in the jam. I may have cheated slightly and spent a little bit of time since trying to go, okay, well, if we have a 64-byte cache line, how many of these structs can I get through? Can I walk through? And so if we move, if I restructure this, suddenly there's room for 2.5 in these. And if I can get rid of one of these floats or something in there, that's it just becomes a nice way of visually seeing what's happening under the hood. And yes, you can do pragma packed aligned and all those sorts of things, but quite frankly, I've been programming C for 38 years. I don't know how to do that, offhand. So yeah, I just thought anything that helps me get a visceral understanding of how this how this works. And yeah, okay, I may be wasting a few bytes up here, but I know if I can find some way to pack this better, then I can get more through the cache line. And yeah, so that's, I feel I'm taking up Leddoo's time here as well.
Yeah,
so
no, we'll get to Leddoo in a
off.
second, but I have to linger a little bit on this. Seeing in action seeing the padding and the overall size of the struct change in real time is like way more of a benefit than I expected just from looking at the screenshots and stuff that you had shared on your Jam project page. Like being able to see like, oh, this fits in the gap and so it doesn't expand, but then this goes in here and naturally like, bumps it down to align this other thing. Like actually seeing that happen as you move it around, like that real-time aspect of it is so cool. And I feel like does a much better job of communicating how that kind of thing works, right? And because like the process of figuring this out on your own otherwise is like printing a lot of offset ofs and recompiling and trying different things, right? So
and getting out graph paper and whatnot.
Right, having to either you have to do it by hand yourself on paper or you have to do this slow recompiling sort of process. So that's really
and
really
even
cool.
to know that it's that this is a thing that happens.
Oh yeah.
And I think this is one of the big failings of my project is that this is a native app that I've it's 600 lines of JAI code, which was great fun to write, but I don't feel like the target the people who would get the most out of this would be if there was a Godbolt version of this where someone who's a little earlier can just go, hey, how does the struct work in memory, can get to a web page and then drag it around on there. So that was was a part where I'm like, okay, yeah, maybe it would have been a pain in the ass to do it in JavaScript.
It's a Jam
CSS,
project, right? Like, there's really no expectation that this stuff is going to be immediately useful for people. And actually, I had some questions sort of on that note, but that's for later because I want to jump over to Leddoo now. And Asaf, if you could switch over to Leddoo's screen share, that'd be great. So Leddoo did this project called Memory Hexplorer, and if you could give us a little rundown of that, that'd be awesome.
Exactly. So you can see my screen here, right?
Yes.
Okay, so my project was basically inspired by this window, which is from Visual Studio Code, which is what happens when in the debugger you open the memory at some address, and then you can see all of the bytes, all of the values of the bytes, but that's pretty much all that you can see. And we know that there are structures here, like the structures we saw from Khrob just now. We know they're somewhere in there, but we just can't see where they are. And so that was my project, basically visualizing that. So let's just show it in action. So basically what my project does is it goes through debug info in a, in the executable. Let me just scroll to the bottom here. And then it figures out, okay, where are all of the things in the program? Where are all of the stack frames of the function calls? Where are the local variables inside of that? And where are all of the global variables, et cetera, et cetera. And then you can go, okay, look here, that appears to be the main function, which has some local variable called node, and it's a pointer which points to this address, and you can follow that. And then basically you can see all of memory and you can just kind of explore it dynamically. And when you open one of these, when you click one of these nodes, you can also see, okay, who's pointing to this? And then you can see, look, it's that pointer over there. Yeah. Let's dive into some questions, I'd say.
Yeah. I mean, this is an amazing result for such a short period of time, right? Like, I was working on something kind of similar, but was doing it all just like you have to write the code that'll sort of dump the structure that you want to visualize. Whereas you just went straight for the debug info and actually got all that working, which is fantastic.
Yeah, not gonna lie, I was quite prepared for the jam as well. I might be working on a project related to this, so
sure.
I had all of the stuff handy and just combined it.
Yeah. Well, I mean, that that goes for a lot of people participating in this. We don't really, we're not too strict about like your preparation for it. Ultimately, it's just a chance to explore new ideas and not to like compete for, who has the coolest project. But this is really a remarkable thing to look at nonetheless, especially because you had a screenshot on your Jam page of some Rust code or the result of running this program against a Rust program.
Yeah,
and
exactly.
the amount of data that was visualized there. I mean, I know it looks somewhat complicated, but I was really struck by still how like readable it is and how well this composes, because you've managed to actually show like the layers of structure in line with memory. So you really are just keeping that sort of hex viewer structure intact, where you're kind of just looking at raw memory but annotated with exactly what you need. Have you like, was there something that inspired this particular design, or just like something you came up with to try and visualize this?
It was something I came up with when I originally proposed the idea on the Jam ideas threads thingy. I came across some extension for Visual Studio, I think, which basically drew the hex bytes and then drew some of the hex bytes in colors to show you that there's some kind of structure here. But I just kind of, as a principle, wanted to be able to see everything all at once, which
Yeah.
I don't know if you can still see my screen, which for the Rust case, that sometimes then results in you can only see 2 hex bytes per page of the screen, but at least you can see everything, right?
Yeah,
That was
well,
what I
and
wanted to have.
and I imagine that you could refine this further if you needed to make some things collapse or
Yeah,
whatever
for
you
sure.
needed to do.
So, yeah, one of the obvious things for Rust is like if you have this cell structure with the unsafe cell inside of it, you don't really need to know all of the structure. You really only care about that the references are 2 in this case, right? You could collapse that in theory.
Right. So these projects seem in some ways similar to me. They're each exploring a different aspect of fundamentally like how are things laid out in memory, right? Khrob's project is looking at individual structs, but then giving you that context for how they fit into cache lines, or otherwise how that size matters to your program. You're showing sort of the live structure of the program in memory and how those same structures are actually represented here. So like, instead of seeing information about the explicit sizing of fields, you do still see the fields here. So I suppose you could still infer that there is some padding in cases where that padding would appear.
Yeah, if there was padding, it would just show the bytes without any label around them. But
Right.
what you can also see, which is kind of similar to Khrob's thing where you can see padding, is where you can see unused space in the memory. Like this, for example, is the heap region, and you can see that there are some lists allocated here, but like half the space isn't actually used. Because
Yeah.
I assume that it's rounded up to the allocation granularity of 16 bytes.
Sure.
That's what I assume.
Yeah, that's really interesting. And I can tell you that like I really wish I had something like this a lot of the time for my job. Like whenever my work requires me to go look at a hex viewer or something, it is just so painful. And there's
you're in for a bad time.
Yeah, and something like this seems like such a natural addition to that, especially. See, I didn't really I would not have believed that you could get results like this with just the debug info that was already there. Like I didn't think that the results would be like so useful. Like I assumed that, well, actually getting at the structure of it is still going to be it's not something you can really do automatically. In my own project, I was trying to give you more like drawing primitives for like how to create your own visualizations. But I was assuming you would need that because I didn't think that you could do like a useful enough automatic view. And this has somewhat proven me wrong on that, because I think that just having this would genuinely make my life a lot easier and presumably not require any new tooling or any new developer effort, which is remarkable.
Yeah, I mean, there are some
It'd be
limits
great.
to it. Oh, sorry. Go ahead.
Oh, I was just saying, it'd be great, if you could click on one of your sections and come into my view and just sort of, drill down further and further.
For sure,
yeah.
And in fact, the question that I mentioned that I wanted to get back to was, it seems like, Khrob, your project is sort of, if I imagine how they would be integrated into people's workflows, yours is sort of on the editing side, Leddoo's is on the debugging side. But I was curious how each of you thought about how you would want, like where you think today's tools are lacking and where you would want to see these kinds of things integrated into your own workflows.
I think from my perspective, I, I've been doing this for a while. I have a rough idea of where all the memory in my program is, but that's been hard-won knowledge. And I feel like beginners and people who are in memory managed systems and that's languages don't have that basic understanding that actually this all goes somewhere and you can lay it out in a logical path. So if I had tooling that was just like, okay, I'm going to assign a memory arena, and maybe there's that sits there, and then I've got my stack arena here, that I can see how they're filling up and emptying as I move through my program, and I can just know that, right, here are all the textures in my game, and here are all the 3D models, and here's the frame information, that sort of thing. Being able to, look at Leddoo's stuff and just go, here's the program as a whole, but I can drill down into that and just go, okay, yes, I can think of this memory address without having to think necessarily of hex values, but like I know I have this much space here that I've given myself to work with, and here are all my vertices, or so that's where I'm coming from a very top down sort of view. I feel like we're sort of hitting things from different different heights.
Yeah. And Leddoo, what about yourself?
Yeah, for me, I think dynamic program visualization, so like actually seeing what's going on in the running program, is something that we're severely lacking in. So like, for example, on the source code side, we have language servers, we have syntax highlighting, we can jump to definition, we can do all of these things to get an idea for the structure of the code. And we can also, in VS Code, you can actually, at least you can inspect fields and you can see their offset and size. So you can kind of build the picture in your head, although Khrob stuff would still be better in that case. But I think on the dynamic program, like on the running program side, we basically, for most of us, we run our code on the command line and then it crashes and we have no idea what happened. Or we're running the code and it's maybe using up more memory than we want it to be, but there's really no way to look inside of it, right? That's kind of what I'm coming at it from.
Yeah. If you've got a leak, it should be really obvious when your green block in Leddoo's things is going do. It's like, oh, that's where it is.
Yeah, that would be fantastic to see. And actually, now that you mentioned that, I wonder how far out you could zoom on Leddoo's kind of view and still have some useful information there. I bet it could work. It'd be kind of fun to explore.
The thing is, it technically is drawing everything right now, which is also why it's a bit slow.
Sure.
But so technically you could zoom out, and then it would be interesting what you would see. You could also expand how many bytes are on each row. That would also maybe. I think that's something I want to explore, actually.
That'd be really cool. Yeah, I mean, I hope that. I'd love to see both of you, continuing to work on this after the jam, if it's ideas that you find interesting. We got to move on to the next guest now. Thank you so much, both of you, for submitting these projects, and also thanks to Khrob for being on the show very late at night his time. I really, really appreciate it.
Almost 2 a.m.
Yeah. Anyway, thanks to both of you, and see ya.
Thanks.
Okay, our next guest is actually also up very, very late. We are now going to take a look at Zeanith's project called ZBiggestProcess. And Zeanith is also somebody who might be familiar to people who have been in the community and watching these jams before. Because Zeanith is actually a returning jammer as well. He's the creator of Z Underglow for last year's Wheel Reinvention Jam, which he was actually also able to bring to Handmade Seattle, which was a lot of fun. And Zeanith's project is actually one of a couple projects this jam that were in some way related to lower level Windows APIs, getting at more information than Windows will typically show you, even though it's actually already there in the system. So before getting into the actual project, I did want to briefly highlight one other project. So this is Process Spy by Taylor Robbins, and this is a project that shows you which projects or which programs are accessing which files. This is information that you can get at through Windows APIs, but Task Manager doesn't show you what files are being accessed by what programs, and that actually might be really useful information to know a lot of the time. So this is a really great example of visibility. And as I said, this project by Zeanith is another great example of that. So, without further ado, welcome to the show, Zeanith.
Hi, thanks for having me.
Yeah, of course. So, your project, I went to the wrong scene. Here we are, ZBiggestProcess here. So, yeah, if you could just tell us about the project, give us a little demo.
Sure. So I initially made this program. I had very little time for this jam, but I've been growing kind of suspicious of Task Manager. I feel like sometimes, it's not really being accurate with you, and it's kind of hiding information. So yeah, I kind of dived into the Windows API and found this method called NT Query System Information, and you can just basically get a list of all the running processes in your system and get metrics about them, right? So right now the app just shows what the biggest one is. So what is the process with the most allocated to the working memory set? And so right now it's unfortunately Microsoft Edge because I had to use that for today's jam. But yeah, you can see just kind of how much it's like allocating and deallocating in real time, right? And this is not something you really get. I feel like you don't really get a sense of what programs are doing when you're running them, just kind of like what they're doing to memory. And yeah, this API also tracks like what was the process that allocated the most memory at any given time. So yeah, that was I think this is a Windows antivirus process. And so at some point it allocated a gigabyte of my system and then disappeared, right? And so like that's the kind of information that you kind of miss without kind of this real-time tracking.
No, that's a gigabyte of actual resident memory.
Yeah, it's the working memory set. Yeah, so
right.
Task Manager. Yeah, I'm not 100% sure of the difference here because Task Manager it reports something lower, but the Windows documentation says working memory set is what's physically allocated. So yeah.
So Task Manager is actually showing you different metrics from even the working set metric that you're seeing here.
Yeah. It's not the working memory set that Task Manager shows you. It's some other value I can show you.
Weird.
If we bring Task Manager, the guy I don't trust.
Yeah, right. Well, so I personally went down a bit of a memory rabbit hole last year because of some stuff I was doing for work, and certainly found that there are a lot of different ways of counting memory if you really get into it, because you've got reserved and committed and working set or resident minimum. But what is Task Manager showing us here now?
It's showing like a subset of that. So I believe it's probably what's most what's committed to the actual memory is what I guess it is. I'm not 100% sure of the difference. But yeah, there's like other metrics that they just flat out don't show you. Like you can see how much page file it's using. You can see threads, total number of processes. Yeah, so like. I don't know why they don't let Task Manager show you this stuff because it's right here, and so
and that's exactly the whole like visibility thing, right? Is it's like the data's there. Why is no tool showing this to us right now?
Exactly. Like there are third-party tools, but yeah, I wish Task Manager should.
Sure, but like, what other information is Task Manager not showing us, right? If useful information about like, because I think just the idea of seeing like the sort of historical biggest allocation, being able to see that kind of thing and being able to dig in further to like what physical resources it's actually using, I think that's really interesting and kind of important. And yet we just don't really see that. But apparently the tools are there.
Yeah, I feel like Microsoft doesn't want you coming here because when you look at the documentation page, I found it pretty funny. So they document the struct here, which is what each process is. But then there's a bunch of fields that are like redacted. They're just like called reserved, and they don't really document it. They don't tell you what they're for, what they do. They just say, "Oh, that's internal. Don't worry about it." And
weird. So there's weird, right? There's data there. It's not just like reserving that space for the future, but they just won't tell you what the data is.
Yeah, so each process basically this is the struct for each process, and you can see things like peak working memory set, and working set peak virtual size, and then they've got like reserved, and then reserved 6, reserved 5, and they have pointers to different things, and I feel like they have more metrics that they're not kind of making visible to you.
Weird.
But one thing I did want to show because it's you've seen Edge this whole time, just kind of going crazy.
Yeah,
But I if you launch a program that I think does much better job at allocating and managing memory, you can just see just how kind of more steady it is. So this is,
Oh.
The Witness, which is like, a full 3D game in a 3D world, and it's basically static, right? In its allocations. And
Right.
I feel like that's a good sign that they know what they're doing. Sorry, my light just fell. That's a good sign that they kind of know what they're doing, right? And
right. So
Yeah.
so I guess I think you mentioned maybe in your project page that Discord in particular was doing a crazy amount of memory allocation and deallocation.
Yeah. When you move the mouse, of all things, I can't show it here because right now it's kind of jank, and I just show the biggest process.
Right.
Yeah, Microsoft Edge is overtaking that. But yeah, if you run this with Discord, you move the mouse, and if you just highlight fields, it'll do a bunch of allocations, and when you start moving the mouse, it'll be more steady.
How many
But I
bytes or
don't know.
kilobytes or megabytes of allocation are we talking about here?
Oh, it's a good 40 megabyte difference is what I was seeing. Yeah, just
On
for
mouse
moving
move,
the mouse.
incredible.
Yeah. And if you start moving it, it'll go to kind of a sleep state or something.
Right.
I really don't know what they're doing.
Well,
But
and
yeah,
this
just
data
changing-
updates so quickly. It's kind of, I don't think you would see that just from what you see in Task Manager, right? Like Task Manager has this like very slow tick.
Yeah,
tick.
I think it's a rolling average. It's updated way slower.
Right. So
Yeah.
I mean that would, even just that alone is kind of interesting that you wouldn't really see. I mean, you can observe apparently that Discord is very rapidly allocating and deallocating memory, but you would never ever see that in a memory graph because it's just going to appear sort of like high but steady, right?
Right.
Yeah.
Yeah. And so you can just they really have real time metrics of your processes, which I thought was cool. I didn't even know like you could just use the API for this kind of stuff.
Well, and that
But yeah.
to me that opens up a lot of possibilities for seeing. I mean, I think memory volatility is kind of an interesting topic, right? Like kind of an interesting metric to be looking at. But are there other metrics within here that you think would be interesting to view? Like if you were to extend ZBiggestProcess now, what sort of features would you add or other metrics would you show?
Well, that's all the metrics they expose for. There's a couple more. There's which I didn't expose, like priority and things like that for your process. I just didn't find that interesting, so I didn't make it visible. But yeah, also quota page pool usage. Honestly, I don't know what that is, so I didn't show it.
I could get my like Windows internals book off the shelf back there and start paging through it and try to figure out what the heck that means. But yeah, it gets complicated.
Right. Yeah, but that's really it for this particular function. I really, if I wanted to extend this, I really wanted to just kind of get the metrics that Task Manager shows, like CPU, GPU utilization. I didn't really know how to visualize that, but I would like more accurate values for this because I don't trust any of this.
Yeah.
But yeah,
if you ever do dig into it and just figure out how it's actually accounting for these things, be interesting to maybe write a blog post or just like explain in Discord, because like I would like to have some amount of confidence in what these tools are showing me, if I'm going to use them for my programming. Anyhow.
Yeah. Like I should do a write up on this actually. I found this quite interesting to dive into.
That'd be really cool. And the other one last question I guess to ask was like, how difficult was this to make overall? It sounds like it was kind of just one Windows API and that was it.
Yeah, it's one function call. Like that's
Wow.
really all I did. It's like 120 lines. It's really nothing.
Well, that's kind of a great reason then for more people to go dig into this themselves, right? Like this information is right there if you want to just like go make some calls and build some tools to display it. It's really nice actually to see that information is so close at hand, right? You didn't have to do anything too crazy to pull it together.
Yeah, no, and pro tip, if you really want to display text on screen real quick, just draw text to the screen window. Just get the device context for the monitor and just use it.
I didn't even know you could do that.
Yeah, I didn't know either, actually. I just kind of Googled, like, what's the fastest way to display something? And I really didn't have much time. So I'm like, oh, you can just draw text with you just call HDC null, and it'll give you the DC to the window. And yeah, to the monitor, right? And then yeah, you just call it and it displays. So yeah, no need to handle messages or anything like that for a normal window. Just display to the screen.
Interesting. Well, that's even better then. Anyhow, thank you so much for submitting to the jam again. Thank you so much for doing this. And again, so Zeanith is in New Zealand, and so it's yet even later for him, I believe.
It is. It's really late.
So I really, really appreciate you being here. Thank you so much for helping us make this show happen.
No, thanks for doing this. This was very fun.
Absolutely. Okay, our next guest is Abec, who is yet another familiar name from these recap shows. And in fact, Abec's Jam project is actually a direct continuation from last year's Jam project that he did. So last year, his Jam project was called Diffest, and it was this idea for a code-aware diffing tool. Oh, my audio cut out? I'm sorry, one moment. I'm seeing things in chat. OBS must have screwed something up on the transition. But as long as I'm good, I'll keep going. Good? Okay. So, Diffest was this code-aware diffing tool designed to diff code instead of just text. And he submitted this to last year's Visibility Jam, but I believe struggled a bit with performance. He's back with Diffest 2, and let's get Abec on here now. And, welcome to the show, Abec. And if you could give us a little bit of a rundown of Diffest and the history of it, I think that'd be amazing, because we've never had a direct continuation of a Jam project before.
Yeah, thanks for having me. Yes, like you said, Diffest 2 is a continuation of the first thing. There were not only performance problems in last year's project, but also result problems. So whenever I compared two code bases where the abstract syntax tree, the AST, is significantly changed, the results were just ugly. So let's say you have a function and a bunch of code in there, and then you put an if around some of this code. Diffest, the original version, didn't get this. The resulting diff looked like shit.
Sure.
And so Diffest 2, I wanted to tackle this problem explicitly. So subtitle of the project is the why and how of comparing trees. And we already talked about the abstract syntax tree as one tree that you have. But also, in software, there are more kinds of trees. Your file system is a tree. There are various data exchange or configuration file formats that are trees, like JSON or XML or so. So comparing is important in all of these, and not only if you're someone who makes a crazy Jam project, but comparing trees is hard. And what does a computer scientist do when a problem is hard? Well, they break it down, divide and conquer. And so I broke this hard problem down into 3 main steps. Step number 1, turning those 2 trees, both trees that I have, into 2 lists. That's trivial. That's depth first. Step 2, comparing these lists. That's also pretty easy. Comparing list was also part of Diffest 1. And I knew the algorithms. And then step 3, turning this resulting compared list back into a tree. I mean, how hard could that be? So comparing lists, what did I use? I used the Wagner-Fisher algorithm. That is the standard algorithm for comparing lists. If you happen to know the Levenstein distance or the edit distance, that's what you usually learn, where you usually learn this algorithm. But the thing is, you build up a whole matrix. There's n-squared complexity. And so I decided to optimize that by trying to pathfind through all these possible comparisons between those 2 lists.
Yeah, if I could pause you there for a second and ask a couple questions. So I saw in your Jam project that you said you actually flattened the tree to a list before doing this operation, right? Is that correct?
Yep. Yes.
And that surprised me a bit, because I would have thought that if you do that, you just lose all the information. So, how exactly does the flattening step help you with this process?
I flattened the trees because comparing these lists and not comparing trees is the easy part of this. The third step is turning the resulting flattened list back into a tree, and that turned out to be harder.
Fair enough, I guess, because I was
Um,
wondering then. I assumed you had to in some way reverse it, but wasn't sure how that would work.
Right. So in the resulting flattened list, or the compared list, for every element in this compared list, I have 2 pointers into the original 2 trees. And in some cases, there's only 1 pointer in there. So if an element was added or removed in this comparison, there's only one pointer in there. And so what I do in order to turn this thing back into a tree, I grab the first node in the list and make that the root node, and then I grab the next node and try to attach it below the previous node, and check if the parents of the previous node are the parents of this, or check if the 2 versions of the previous node, like both original versions of the previous node, are the parents of this new node. And if not, I walk up the tree until I find these parents. Now, there are various edge cases with that. So for example, let's take the chance and look at the screen share I've brought with me.
Yeah, and I was going to ask, I couldn't quite understand from just the screenshots what we were seeing here. So is each row a test of your algorithm?
Right, exactly. Each row is a test case. And then the left column is one side of the tree, so the original tree, and the middle column is the second tree, and the last column is then the result. And like the first few test cases are pretty obvious. And then I have some test cases where I added or removed an entire subtree, and it marks that entire tree as removed.
Mm-hmm.
And then these sort of test cases is where it gets interesting. Here we have a node that gets added, and in this case, I try to attach this node to the parent node, and then actually check that that's the correct place, and then in this case attach it there. And then the third node I would try to attach to the previous node, but that's not the correct place for it. And then I move up until I find the actual root node where the bar node here belongs and attach it there. And that's how the result gets turned back into a tree.
Mm-hmm.
And especially with stuff like here, for example, we have a node in the middle that gets added. All of this then are various types of edge cases that need to be handled properly.
So in a program context, that would be like wrapping a set of statements inside of an if, right?
Exactly. This is exactly this case. The bar would be the if in this case, yeah.
Interesting. So you flatten it to a list. You run this Wagner-Fisher algorithm, you said?
Yep.
And you had some interesting stuff in your project submission about running A* on this algorithm to navigate the space more quickly, which I thought was interesting. And then
which turned out to be worse in the worst case. But
oh, really?
Okay, whatever.
Well, I mean, of course, the worst case is worse with something like that, I would assume. It's maybe not too surprising.
The interesting thing is, you could probably improve it so that the worst case is actually as worse as the Wagner-Fisher algorithm, because both the Wagner-Fisher algorithm and there's an optimization on A* for when you're only operating on a grid. If you've got a pretty regular grid, then there's an optimization for A*, and that is basically the same thing as Wagner-Fisher. And so I probably just need to implement that, and we would have a better worst case.
Well, that seems
But I didn't have
promising.
time for that during the jam.
Oh, fair enough. I mean, this is a lot. And so you flatten it to a list. You run this edit distance kind of operation on it.
Yep.
And then you actually are able to reconstruct the structure by taking the linked list nodes, but then correlating them against the original left and right structures that you were diffing. So
Correct, yeah.
What's the difference, I guess, in quality between doing sort of an edit distance thing on a linked list and the edit distance that is presumably happening on text?
There are various edge cases, especially, let's see if I have, oh yeah, right here, next one. In this case, I moved this final node below this one. Now, as you can see, if you just look at the order, those are the same order. So there isn't actually a difference in this compared list. And so this is something that the diff only shows up once you actually build this back. And in this case, it looks like shit because this foo and this foo are actually the same foo. That's just the way I'm displaying it. And there should be a better way to display this, but I haven't figured one out yet.
Oh, but your algorithm did actually resolve them to the same thing.
Yes.
Okay, interesting.
Like,
oh, and I
they have-
suppose in a real system, you would be able to provide a unique ID or something to every single node.
Yeah, and like it should be correlatable. Like, I'm doing this below where I find a node that got moved and mark it as the same thing. But yeah,
I see. Interesting. Well, this, I mean, I have to say, the examples that you're showing here, I mean, they are, you're calling them edge cases, and, you know, from a diffing point of view, I suppose they are. But they also look like exactly the kind of cases that you would encounter if you were trying to do this against an actual program, right? Like you're showing, when I look at this, I see examples like wrapping something in an if statement or moving something outside of an if statement, right? There's really common operations that you would do to like a syntax tree. And I believe that was the original motivator for this, right?
Yep.
So is this, in your estimation, ready to start applying to real ASTs, or is there more groundwork that would have to be laid before you could start actually applying this algorithm to real programs?
Like, I found a lot of these cases, like, sure, let's not call them edge cases in that way. But like, there are various places where it doesn't work. Let's see. For example, this one. Here I moved the bar easy out of foo. In this case, I've got two foos, which is technically correct, but practically not pretty. And if I put enough people in between, enough nodes in between, the entirety looks better. So there are a few more cases that are weird, and there are also a few cases that make the entire thing crash because it doesn't find a parent for some reason. So those are not on here for obvious reasons. But yeah, I guess if you decide to, deeply fuzz test this thing in order to ensure that it doesn't crash for stupid inputs, then yeah, I think it produces pretty good results for pretty many cases.
Yeah. Well, this is really exciting. I'm really glad that you took another crack at it and were able to make some progress, because I really do think that something like this would be a huge improvement to so many tools if it could become widespread. So it's really, really great work, and I'm so glad that you took another crack at it.
Yeah, sure.
Thank you so much for being on the show. Really appreciate you as always. And with that, we are going to go over to our final guest for the day. Our final guest is Alan Webster, who is one of the longest standing members of the handmade community. He is the author of 4Coder. He is a former Rad Game Tools employee and now an independent programming researcher and content creator, and more on that later. Alan's project this year was a plotter for differential equations, and he actually streamed all the work for this project over on his Twitch channel, Mr. Fourth Programming, which I hope Asaf can grab the link for here and paste it in the chat. But without further ado, welcome to the show, Alan.
Hi, thanks. I'm gonna show this first because it's pretty, and that's a good place to start. And then I'll tell you a little bit about what motivated it. Okay, so this is what it looks like. It's not honestly in very much of a tool status yet. You couldn't use this for a lot, but where I'm really getting interested with visualization stuff leading into this project is thinking about how to use motion and animation in a visualization, because that's something that is uniquely computer possible, to create motion to visualize something. And actually, one of the ideas I wanted to explore was to create an animated task manager. And I was spooked off by the idea of having to figure out the APIs for that. But with the work Zeanith did and the results we got, I'm like, oh, that's definitely a project that needs to happen. We need an animated task manager for sure. But I ended up going with this because it felt a little more accessible. And I learned a lot, one, about the differential equations that I was exploring, and also about what it kind of takes to make this particular style of visualization. The tool itself just has a few built-in equations you can do, and you can like look at the details for any of them to learn a little bit more about the math and the model behind it, and tweak the parameters. You can do stuff like, hey, I want to see what happens if the prey species, and this is a predator prey model, I want to see what happens if it grows 4 times faster, and you can see like we get a different plot.
Ooh.
But there's not enough direct interactivity in my code base to make this better yet, but I'm hoping someday to be able to like build and model systems like this more interactively and visually. So this was a first step towards that kind of stuff.
Yeah. So what was the motivation for these differential equations and things? Were you just researching differential equations for some other reason and just wanted to visualize them?
Yeah, so I saw there's a topic I've gotten interested in different that uses a differential equation. It's actually one of these. Let me look at my list here. The replicator equation is an equation used in a field called evolutionary game theory that I was curious about. So I wanted to make a visualizer for it, and this is only a one-dimensional, so the y-axis doesn't get used here, but it's showing the equilibrium point here in the middle between two different strategies in a population competing with each other in a in a way that sort of uses game theory combined with this idea of a replicator equation. So I wanted to part of the motivation was I just wanted to see this, but I also am curious about the idea of modeling sort of continuous functions or modeling mathematical ideas. I don't want to make a programming language out of that. I want to make like a visual modeling thing. You know, we use things like Bezier curves and interpolation things when we're making animations. And I just want to make like a highly intuitive, visual, interactive, like continuous function editor someday. And this stuff like this feels like a part things I need to learn and get my head around better to approach that fully.
Yeah, that would be fascinating. So I had seen vector field and flow stuff like the predator prey example and like this one, I suppose, because like when I did my very little bit of differential equations and multivariable stuff in college, you know, that was the type of function that they were showing, and you can draw a static image with all the arrows. But you had another demo that you showed on your project page where everything was like crossing in the middle, and I was immediately struck by like, hold on, I don't think you can draw a vector field like that.
Yeah. So what happens with this one? This is a three spring system. So it's modeling two masses, and this is not the great visualization for it because you can't see two masses. We got the position of one mass is the x coordinate, and the position of the other mass is the y coordinate. So it's an inappropriate visualization in a lot of ways, but it lets you see lots of these systems simultaneously. And what it highlighted for me, this is going to touch on the differential equation terminology real quick, but I think the visualization makes it a lot more intuitive, which is that if we look at the details for something like Lotka Volterra, which is the predator-prey model, this is a so-called first-order equation. It means that our equation tells us the velocity of x and y given the position in the field. Whereas if we look at the three-spring system, what we have is three springs operating on two masses that are like connected in a chain. And so that gives us the acceleration given the x and y position. And that means that I'm actually separately modeling a position and velocity for each point, which I learned a number of things. You have to program that differently. The way even just numerically evaluating this isn't the same because it's second order. And you can also, as you pointed out, see the difference. Like it no longer feels like a coherent flow field. It feels like this system of well, more like a gravity simulation might look like this. All the things are flying near each other, although the math behind this one isn't gravity, so they're not attracted to each other. But the point is you can get an intuitive feel of like, okay, that can't be a first order. This is, I can visually feel that this is something more complex and chaotic. And there's some problems with visualizing this, right? The flow fields, if you do some tricks to spawn in and kill off particles to keep the density of the particles even throughout the field, you get a good view of what's going on. But here, all of the particles spawn in with zero velocity. So we're missing all kinds of things. Like what if I, instead of spawning in random positions, I spawn them all at the same position, but with random velocities? What can I trace out there? And so this is probably an inappropriate visualization to understand the system, but at least visually communicates to me that a second order equation is very different from a first order equation.
For sure. I mean, I immediately intuited that, I think, just from looking at the videos, which is saying something. And it seems to me that you could fairly easily add some interactivity. I can imagine like dragging the mouse to sort of spawn particles in with the velocity of the mouse, and then you could see how they react from there, and that could be interesting. There's that. There's also, I mean, all of these are pre-programmed, but there's no reason why you couldn't, with a good interactive system, sort of make a bytecode interpreter to run your, like, you put in the equation yourself, and then you'd have a lot more freedom. But 3 days I was already working on fine-tuning all the particle effects to get the visualization right. I wasn't going to do that too. Yeah, of course. And I would also like to ask, what kinds of things did you have to do to make the visualization work right? Because you said that there was maybe more to that than you might initially expect.
Yeah, so I mean, at the lowest level, and what I spent the first whole day on, plus a little bit of the second day, was just getting the trail effects just right. Because I wanted those trails, like I wanted a nice API that gets that right, and um, making sure there aren't bugs where like particles that are supposed to be dead sit there. I think on the first day I posted a GIF where there's like little like dust everywhere because particles that are supposed to be dead are still rendering stationary points. So fixing all that just to get the particle effect was part one. And then two, there's this, like right here, there's still a problem. There's a little bit of a gap. The system spawns particles in randomly every like 5 per frame or something like that if there are free particle slots in the particle system. But you can see like here, we don't get a lot of detail, whereas like everywhere else, the density is higher. And that's because particles here move away fast. They're moving fast in this direction. And they're not spawning here fast enough to keep it full. So a big part
I
of this
see.
was
So
trying
the
to keep
density,
even.
yeah, the density of the field is not even, I suppose, just because of.
Yeah.
Well, I suppose maybe if you just like rendered bigger and cropped in, it might, something.
I mean, yeah, there's more to explore. The things I do have is like, since it's spawning in particles, because we also have particles exiting the system, and when that happens, we want to put them back in so that we don't just lose all of our particles and have a few in the middle left over. We also have spots where they get so slow that they would all bunch up there. And so what happens is every frame it's looking at all the particles, and if the area around a particle is getting more and more dense, it has a higher and higher probability of killing that particle off, and then it spawns them in just random. Right now it's just uniformly spawning them in. I could have done like analyze the areas where the density is low and spawn more there, but I haven't gone far enough, in my opinion. But this was pretty good progress on like figuring out how to balance out the spawn and density maintenance for first order stuff. For second order stuff, it turns out all the density rules had to be different because 2 particles in the same spot might be going in opposite directions, and you don't want them killing each other off. Yeah.
Right. Yeah. Well, I think I'm sure there's some room for improvement, but it's already, I think, an excellent visualization of this kind of thing. Like it does seem pretty well balanced and seems like it does a good job of communicating the overall shape of the field. And I believe you even, I mean, you had a video on your jam page of the sort of the center of this predator prey thing moving around as the growth rates change. And I thought that was really kind of fascinating to see in real time, because like, I mean, you just don't see that outside, you can't get that sense in a textbook, right?
Yeah.
And that dynamic nature of it is just really, really cool to see.
Mm-hmm.
So, and I'm going to start my segues now. So is this built on your Mr. Forth code base?
Yeah, so that's part of why it doesn't have a lot of interactive stuff yet. I haven't really built in UI, but this is all my Mr. Forth code base stuff, and it's not open source yet, but it is all, since you're segueing into it, I have a membership program and there's exclusive source access. So stuff like this that I have not refined enough to make it open source, you can get like early access and check it out. And if you want, you could even ask me for a license for code like that if you're on the membership program. And I also do like weekly devlogs where I explain a lot of what I'm working on. So yeah, this is how I am funding now. Is anyone who's watching, if you think that what I did there was cool, or my streaming or stuff on my YouTube, I am keeping all of that going full time by counting on people getting involved in this.
Yeah, well, and you've got a lot of interesting projects in the works that you talk about on your homepage here. So, what sort of other projects do you have coming up that you're going to be working on?
Well, the one I'm really diving into in the last few weeks is my binary file, object file stuff. I'm actually going to make like a program where you can grab your exe or your PDB or your DLL or your Linux versions of those and drag and drop them in and start visualizing the structure of that, sort of like what you would get from a reverse engineering debugger, but more to the eyes of like seeing how linking architecture works, seeing how like it's almost like a giant visualizer project that I'd like to spend a lot of time on, like really illuminating how all of the native layer stuff is working. I'm also pouring a lot of time into making my base layer into a reusable library, and some other stuff which is happening here and there in the background, like making arena use videos and stuff like that. So that's what I've got going on.
Cool. Well, and to continue the segues, we've got some other stuff. Or sorry, I forgot my audio gets garbled on the transitions. We've got some other stuff coming up, and in fact, Alan does too. So, Handmade Boston is coming up in less than a week now. The conference starts on Friday, this coming Friday, August 9th. And if we scroll down here, Handmade Boston's going to have several amazing speakers. The format of the conference is these masterclass sessions, so longer than you would get from a normal conference talk, and getting really deep into some technical info and other sorts of wisdom. The speaker list is fleshing out really well. Abner has told me that he will be publishing the conference newsletter today, so make sure that you pay attention to that and go sign up for the conference here. But if we click over here on the speaker list, we've got, Billy Basso, Zach Nowicki, Kaze. Oh, and look who's this. Alan Webster, founder of Mr. Fourth Lab here, is going to be speaking at Handmade Boston. So if what's your session going to be about?
Well, I'm going to be collaborating with Abner. He's been working on Terminal Click, and we did a podcast about it and a couple of streams about it. And so we're going to spend another couple of hours on stage understanding the architecture of terminals, and specifically the architecture of Terminal Click, and talking about how I analyze architectures of things and how I then use my understanding of an architecture to improve the options of could we open up possibilities to go in this direction. I apologize about that. But yeah, we're going to be just basically diving into the architecture, how he's put together the whole program so far, where he might have room to open up new possibilities by looking at that architecture analysis. So yeah, it's going to be fun, I hope.
Yeah. So everybody can go get tickets to Handmade Boston. If you can attend in person, you're out on the East Coast, that'd be amazing. There are also online tickets available, and several of the Handmade Boston sessions are actually going to be online only, including Kaze's. So really encourage everybody to go check that out. And if you buy a ticket, you'll get access to the recordings from the conference as soon as they go up. So highly recommend that. All right. Thank you so much for joining us, Alan. Thanks for submitting a project to the Jam and participating as always. Thanks for all the hard work that you're doing.
Yeah, thank you.
And with that, we're going to wrap up here. Thank you so much to not just the 6 people who have demoed their projects here today, but to all of the people who participated in the Jam and all of the people in the community who were, sharing their thoughts and their feedback and their ideas as this whole thing was running. It is always a fantastic time to run these jams. I'm always amazed by the quality of the work that people can do in such a short amount of time. We have so many incredibly talented programmers in the Handmade community. It's just absolutely amazing. I've got a few more things to plug before I go. So, right here on our Twitch channel, we have a show called Unwind, where once a month we interview someone from the Handmade community about their work, much like this, but going into more detail. So BYP, Billy Pan, was on Unwind a while ago talking about his further regular expression work, for example. We had Yasser, oh no, I can't pronounce his last name. We had Yasser on to talk about his compiler work and his backend engineering work. Our next Unwind is coming up on August 17th. That will be 2 weeks from today, 1 week after Handmade Boston. So if you are not yet, please follow this Twitch channel so that you'll get notified when we go live for that. And we also have one more jam coming up this year. We are going to do one more wheel reinvention jam. I shouldn't say one more. We're doing another wheel reinvention jam, one more jam this year, and it's our annual wheel reinvention jam. That's coming up September 23rd through 29th. That is a week-long jam, like we've always done for the Wheel Reinvention Jam. We would love to have you join us for that. And so if you would like to be notified about more information about that jam and other events that we have going on, please visit the URL. Let's see. Asaf, can you post the up? I'll post it. I've got the chat up. You can visit handmade.network/jam/upcoming. And this page has the details about our jams and a link, or a form, to sign up for our email newsletter. So if you're not signed up for that, we'd love if you did, so that you can make sure that you keep up with all these events that we've got going on. And so with that, finally, the show's over. Thanks again to everyone who joined us, especially those 2 who joined us incredibly late at night. Really appreciate it. And we will see you again for Unwind in 2 weeks, and then the Wheel Reinvention Jam in September. Bye, everyone.